Okay. Sound check. Yep, sound check's good. Time started. Let's have a look. Is Twitter on ball? It's just a little bit behind, still scheduled at the minute. Right, X is live as well now, so we're all good. So let's quick check. Right, we'll get started in a second. Okay, right. We're all set. Let's get started. So, oh, this might have been the week that we finished this off, but let's figure out. Let's find out if tries and graphs, breadth first search, depth first search, and then whatever. I'm not even sure what P versus MP is, to be honest. Let's see how we do getting through this. We got a couple hours tonight. This might be us finishing two chapters, and if we manage that, like, I mean, let's see how far we go. We might get further, you know. We might finish it. We might go all the way. Might get all data structure and algorithms done, and then next week we look at starting something different. We're starting something new. We're starting memory management in C, which is going to be a roller coaster for me. I ain't gonna lie. And then from there on out, at least the number of lessons that come into things and stuff is a little bit small. I mean, I say smaller, gigantic, medium sized, like smaller, but it's going to be a project. It's going to be a little bit more big project, so bigger, like, you know. But we'll see. Like, you know, I wanted to try and get through all this by the end, in a year. So it's August now, so just got to really hit the grind and go for it and stuff. Maybe we get to this stuff. It'd be good if we did, but we'll see. We'll see about it. So, without further ado, I'm not even gonna lie. I never even heard of tries. I don't even know what tries are. So, tries are one of my favorite data structures. I've used them often in the past for natural language processing tasks. In Python, is it try or how do you say it? I'm guessing try. Not to be accused of try. Tree. Okay, but not tree in the tree sense. But not tree as in spelled in the normal way of spelling tree. Okay. So trees are one of my favorite data structures. I've used them often in the past for natural language processing tasks. In Python, a tree is easily implemented as a nested tree of dictionaries where each key is a character that maps to the next character in a word. For example, the words hello, help, hi would be represented as, okay? All right, okay. Yeah, so HELLO is true. HELP is true, yeah. And then hi, HI, yeah, okay, cool. The asterisk character paired with true instead of a dictionary is used to indicate the end of the word. So a tree is also often referred to as a prefix tree. Is it meant to be spelled that way? Like, because he's then saying tree in here and stuff, so I have to ask Lane that one. In fact, I'll take a screenshot. Where would it go? Downloads. Where'd the screenshot go? Pictures, desktop, documents, downloads. Did I even take a screenshot? Control Shift, print screen. Whoops. Control, print screen. I think that's done it. Hold on. I have to look up my thing again. Config i3. Control print screen. Control mod print screen. Control shift print screen. Okay. No, that's the one where you do selection. I don't want to do that. Control mode. Okay, I think that was the one. Where'd it go? Hold on. Home users pictures. Shift print screen. So it goes to pictures. Home user pictures date. Hold on, let me switch over for a second. So weird that I can't put an image in. Alright, I can just do print screen, it just goes to my copyboard. Okay. Right, so exit that. Okay, right, let's come back to it. All right, diversion over. Okay, so we think of that. Okay, so we understand that. So a tree is also referred to as a prefix tree because it can be used to efficiently find all the words that start with a given prefix. Assignment. We're going to use a tree to add prefix searching to locked in. For example, a user will be able to type dev into a job search bar and see autocomplete suggestions, developer, development, DevOps, etc. Complete the add method. It takes a word as an input and should add it to the tree. Okay, so keep track of your current level in the tree starting at the root. So current level goes at the root. I don't know, like to put out a 0. Loop over each character in the word to add. So for letter in word, if the character is not a key in the current level, what? Keep track of your current level in the tree. The character, so if letter not in current level, then add it and create a new nested level dictionary for it. What's up, peeps? I can see if you join the chat. How you doing? Update your current level to the new nested. So if the character's not a key in the current level, add it and create a new nested level dictionary for it. Update your current level to the new. Okay, keep track of your current level in the tree. Oh, right, okay, hold on, self.root. Okay, update your current level. So if the character is not a key in the current level, I'll add it and create a new nested level for a dictionary for it. So I guess current level. I do like I append to a dictionary. Like I forget. Not familiar with them yet. So dictionary. Can I just do? Can I just do this? So I can just do like, oops, like that. And update your current level to the new nested dictionary. All right, okay, I see, right. Current level equals yeah, it's a little bit weird this, but I understand it. I think that's right. I think that's right. I think that's right. Whoops. I think that's right. Once you've ensured all the dictionaries exist, add the self.end symbol to the dictionary of the last character in the word. This will indicate that the complete word and not just a prefix in another word. Okay. So I guess it just happens at the end after the loop anyway. So I guess then current level I guess I could just be current level self dot end symbol, is it? Is equal to true, like that. I think that's it. Run it. Womp womp womp. Nope. Alright, let's see. So words, expected tree, actual tree. So if the character is not a key, okay. Hold on. How do I check? Oh, here we go. Checking existence of a key. Letter not in current level. I guess it worked, but when it went back around again, where's mine falling down? So at that point, it should have been all three of them have got the same thing, so that it should have been that it started there. Huh. Right, so some nesting not working here. It's not. Some of it's working. Is it? No, it's not at all. QA ops, QAM. No, it's not quite working. Right, hold on. Let me read the thing again. So keep track of your current level in the tree, starting at the root. So current health is self root. Loop over each character in the word to add. I'm pretty sure that just works, right? Let's check. Yeah, it is, yeah. It's working as expected. So then, that's right. If the character is not a key, in the current level, add it and create a new nested level dictionary for it. Update your current level to be the newest nested dictionary. Once you ensure all dictionaries exist, this will indicate that this complete word and not just a prefix of another word. So indicate that this is a complete word and not just a prefix of another word. Can't touch bullet line, so might as well hide it. What up, people in the chat? Let me know if you guessed the answer before I have. You know, I might be being a bit of a dummy. HI. Keep track of your current level in the tree starting at the root. So yeah. Loop over each character in the word to add. Yeah, pretty sure that's right. If the character is not a key in the current level, add it and create a new nested dictionary for it. So that's that part. So it's not in the current level, then current level letter yeah. Update the current level to the new nested dictionary. New nested dictionary. Pretty sure that's right. So current level is the new nested dictionary. That's the one that's created in there. And then once you've ensured all dictionaries exist, add the self.end symbol to the dictionary of the last character in the word. This will indicate that this complete is a complete word and not just a prefix of another word. Right, did I get even close with like one of them? Oh, hold on. I don't think it's explained properly. So that's not in the if statement. Now it's going to work. Boom. Yeah. Okay. A little bit misleading. The if statement was just on one line of that description, so that kind of threw me off. But anyway, let's speed up. So exists in a tree. Hello, help, and hi would be represented like this. We want to be able to see what words have been added to the tree. Complete the exists method. It takes a word as input and should return true if the word exists in the tree and false if it doesn't. So starting at the root of the tree, assign the current dictionary to a variable. So current dictionary to a variable. Okay, loop over the letters of the word. So for letter in word, if the current letter is not in the current dictionary, return false. So if letter not in current dictionary, then return false. Update the current current to point to the dictionary at the letter key. So then current dictionary equals once you get to the last letter return true if n symbol is in the current dictionary. So return false if self.end, is it something like self.end symbol? End underscore symbol. Boom. That was a lot simpler. I get stuck with that hiccup with the if statement. Okay, so prefix matching. Oh, important job of the night. Hold on. Important job of the day done. We're back, folks. Okay, so we're here. We're steamrolling through this, so let's get cracking. Prefix matching. Trees tend to be most useful for prefix matching. For example, if you want to find all the words in a dictionary, then start with a given prefix, a tree works great. Autocomplete, keyword search, and spell check are all good examples of where a tree can be useful. Remember, a hash table is also good for exact matches, whereas a tree allows you to look up all the words that match a given prefix. For example, whoops, get the light back on. There we go. All the examples of a given prefix, for example, given this tree. We could quickly look up all the words that start with hell and get hello and help. Hash maps are used for exact matching, prefix matching, suffix matching, all of these, I guess. No? It's only used for prefix matching. I guess it's actually exact matching. Checking whether or not a word exists in a tree is order M, where M is the number of words in the tree, number of points in memory, the length of the word. Words with a prefix. Okay, so in a tree, hello, help, and hi will be represented as this. Complete the search level function. The recursive function collects all complete words starting from the current tree level. It takes the current directory level, the accumulated prefix so far, and the collection of words found. So check for complete words. If the current level contains an end marker, add the current prefix to the words collection. Check. Okay. Complete the search level function. The recursive function collects all complete words from words starting from the current tree level. It takes the current directory level, the accumulated prefix so far, and the collected words. Collected words found. Check for complete words. If the current level contains an end marker, add the current prefix. So start with the if part. So if the current level contains an end marker, so current level end marker self dot end symbol in self dot end symbol in then add the current prefix to the words collection. Then add the current prefix to the words collection. So words dot append current prefix. Process each character in the current level. Process each character in the current level in sorted order. Hold on. To get keys. So characters equals current level dot how is it? How do you do it again? Is it keys? Yeah, dot keys in the current level in sorted order. That's just the sort function. Sorted, okay. For each character, except end markers for each character in characters. Extend the prefix with the current character. Extend the prefix with the current character. X plus character. Recursively search the child level with the extended prefix. So then self dot search call level. Level. With the extended prefix. So extended prefix equals extended prefix. return all words found. So I guess return words. I mean, I guess we're not going to be able to sort of see it just yet. So I'm pretty confident on these parts, but I guess we will come back and see if I get it right. So complete the words with prefix function. So this finds all the words in the tree that begin with a given prefix. So create an empty list to store matching words. So matching words. So just a list. Keep track of the current tree starting at the root. So current tree, current level, self dot root. Iterate through each character in the prefix. So for each character in prefix, if the character doesn't exist in the current level, so if character not in current level, return an empty list. No word starts with this prefix. Return like that. Move the child level. Move to the child level corresponding to the current character. Move. So move to the child level responding to the current character. Okay, so current level equals current level, then character. By now, the current level should correspond to the last character of the prefix. Use the search all function to find all words starting from. Okay, so return self dot search underscore level, and then what do we need to give it? Use them. Find all the words starting from this level. So we need current level, current prefix, and words. So current level prefix, and then matching words. So an empty list to match, store matching words, keep track of the current level, starting with the root. For each character in the prefix, if the character doesn't exist in the current level, return empty list. No words start with this prefix. Move to the child level corresponding to the current character. By now, the current level should correspond with the last character in the prefix. Use the search all function to find all the words starting from this level and return them. Yeah, I'm pretty sure that's spot on. There's some infinite loop going on though. Some return not happening. Let's have a look at this part. So let me just double check this again. So check for complete words. So if if the current level contains an end marker, add the current prefix to the words collection. I'm pretty sure that's right. Process each character in the current level in sorted order for each character except the end markers. I guess Python remove type from list. I guess remove self.end symbol. Does that make a difference? Let's see what characters look like. Characters. Oh, I need to reload. Is it something with the? Oh yeah, there was something with the server. I definitely killed something. Oh my god. Whoosh. Okay. I kill. X9 list. each character except end markers. Just goes on infinitely though. Okay, so do that. And then, so for each character, so then I'll print character. Whoops. Oh no, I keep killing the server lane. Sorry. Alright, let's see. Get it running again. Whoops. I'm not doing it on purpose, I promise. So for character in characters, so then it's just looping around, it doesn't go past the first one. First time pass. Okay, so extended prefix. Let me check that part. So extend the prefix with the current character. The current prefix plus character rather than modifying the prefix in place. So extended prefix, and then it's going to be recursively search the child level with the extended prefix. So current level, extended prefix, words. Return all words found. Let's see what the extended prefix is. So extended. Oh my gosh. Yeah, okay, this is why. Extended DES, DSSS. Extend the prefix with the current character. So current prefix plus character. Cursively search with extended prefix. Oh, whoops. Is that why? So I can't do that. Python remove from keys. I don't want to delete it, I just want to not thingy into it. So sorted. Python remove item from list. So I can just do it in here. So if character is self dot end score symbol, I guess is not. Then do this. There we go. Just need to get a little bit right here and there. Everything falls into place. Bingo. Find matches. So tries are super efficient when it comes to finding substrings in a large document of text. For locked in, we want to be able to find all the instances of bad words in chat messages and fill them out. If we just split on white space and matched against the dictionary, we would miss substrings. For example, if we had the word darn in our dictionary, we would allow the word darn it to slip through undetected. That's why we'll use a tree. Assignment complete. The find matches method. It takes an entire document string as input and returns a set of all the words from the tree that occurs in the document. So create a new set to store the matches. So matches equals set. I don't remember how to use sets, to be honest. Hold on. Python set. Python sets. Right, now to use interest. Set. It's an unordered collection of unique item elements. Also supports operations that differ from those types. Say it's an unordered collection of unique hashable elements. Okay. Loop over all indexes of the characters in the document. This value marks the start of the substring. Loop over all the indexes of the characters in the document. This value marks the start of the substring. So for loop over all the indexes of the characters in the document. This value marks the start of the substring. Okay, keep track of your current level in the tree, a dictionary, starting at the root. Okay, so current level equals self dot root. Use another nested loop to iterate over the indexes of the characters in the document. Loop over all the indexes of the characters in the document. This value marks start substring. Next, you use another nested loop to iterate over the indexes of the characters in the document, but start at the current index of the outer loop. So say outer index, and for use another nested loop to iterate over all the indexes of the characters in the document, but start at the current index of the outer loop. Is fine, Max. Okay, loop. Start at the current index of the outer loop. Let me read the rest. So use if the character is not in the current level, break out the inner loop. There are no matches. Otherwise, move to the next in the tree based on the inner character. The inner character's level contains the end symbol. Add this substring to the matches. You can calculate the full substring by slicing the document using the indexes of the outer and inner loops. Okay. Use another nested loop to iterate over all the indexes of the characters in the document, but start at the current index of the outer loop. I just start at the current index, like or read that. Use a nested loop to iterate over all the indexes of the characters in the document, but start at the current index. Start at the current index of the outer loop. So if we do range in a index, so range, and we say whoops, range is whoops, wrong part. Start, stop, and step. So I think it's roughly that. If the inner character is not in the current level, so if I guess document in an index is not in current level. Break out of the inner loop where there are no matches, so break. Otherwise, move on to the next level in the tree based on the inner character. Matches. Otherwise, move to the next level in the tree based on the inner character. So otherwise move to the next level in the tree based on the inner character. So I guess current level equals, whoops, current level inner, if the character's level contains the end symbol, add the substring. So if the inner character's level, current level contains the end symbol. So if self.end symbol in current level, if the inner character's level add the substring to the matches set. You can calculate the full substring by slicing the document using the indexes of the outer and the inner loops. Yep. Okay, so then matches dot append, and then it'll be document. Slice it like that. Yeah. So it'll just be document append, and it'll be outer index, inner index. Okay, like that. Kind of failed. Whoops, not comma. Range 0 to length of document. Python add to set add. Okay. Where is it? Oh, it's close. Very, very close. It's just missing the last letter for some reason. Start at 1. No, that's right. Let's have a look at that solution and see if it's sort of similar to ours. Yeah, so there's kind of the same. J range at length. Yeah, they had 2 plus 1 at the end as well. Yep, cool. Okay, pretty much the same. Well, this was a little bit more tricky than I was expecting, so we're going to get through 2 chapters tonight, I'd imagine. If we get through graphs as well, that'd be good. What have we got? We got a bunch of reviews. Right, let's review the code we just wrote. So that. What's the big O complexity of find matches method? Let's have a look. So at least n squared, really. O to the power of n squared, where n is the length of the document. O n times m, where n is the length of the document, m is the length of the tree. No. O n times log n, where n is the length of the document. Oh, pretty sure it's that. No? Oh. N times m. Explain why. Of course, let's break it down. The big question was, the correct answer was O n times m, where n is the length of the document, m is the depth of the tree. Here's why. The method loops over every index in the document for in range length document. That's up to n iterations of the document. For each start position, it starts at the root of the tree and tracks each character from I onwards, so like that. But the inner loop only continues as long as the tree path can be followed. In the worst case scenario, the tree is depth of m, so the code could examine up to m characters. Why not O to n squared? If the trie was as deep as the document itself, so nm, then O times nm would become O squared, O to the power of n. But in general, the tree's max depth could be less than n. Depends on the set of words stored in the tree. No, okay, that makes sense. So sort of, I had the right thing, but just in reality, practicality, doesn't make sense. Why don't we just use a simple dictionary lookup to find out if substrings are in the document? Because we need to check every substring in the document, but using a tree allows us to bail early on each given starting character. Because dictionaries don't use hash maps under the hood, because dictionaries are too slow, it comes nah. Because we would need to check every substring in the document, but using a tree allows us to bail earlier on each given string character. So, 2 more lessons in this set. Longest common prefix. Heyo, people. I can see you in the chat there. How you doing? Hope you're having a good night. Bit of a headache so far, We're doing all right. We're getting through. So the longest common prefix. Let's use our tree to find the longest common prefix of a list of words. This feature can be used in locked in to display suggestions when users are searching for their connections. Assignment: complete the longest common prefix method. It returns the longest common prefix among the words in the tree. Initialize a variable current that references the root of the tree. So current Hey Guitar Jams, how do I like this compared to LeetCode or other Leet sites? Well, this isn't really a Leet site, to be honest. I've not really used LeetCode before either. If you're talking about Boot.dev in general is not just data structures and algorithms, but if you talk about this module, I haven't really done like leak code before either, but this kind of introductory and like learning is pretty good. So initialize a current variable that references the root of the tree, so self.root. Initialize a variable prefix with empty string. Enter a forever while loop. What? While? Can I just do that? While true. While true. Get the children keys in the current dictionary. Get the children keys equals current dot keys. If a child is an end symbol, break the loop. If there's only one child, append for key in keys. If a key is self dot end, it's got a symbol, then break, not breakpoint. If there's only one child, append the character to the prefix string and update the current dictionary to point to the dictionary. Luminek. If length keys is equal to 1, then if there's only one child, the child is an end. So if there's only one child, append the character to the prefix string. Number of children equals 0. Guess number of children plus equals 1. I guess at the end of that. So if there's only one child, append. So if number of children is equal to 1. If there are multiple children or no children, break the loop. Term prefix. Okay, this is a bit funky, this, so done that. Enter a forever while loop. Get the children keys in the current dictionary. If a child is an end symbol, break the loop. If there is only one child, append the character to the prefix. If there are multiple children, no children, break the loop. What? get children keys in the current directory. If a key is an end symbol and break the loop, if there is only one child, the child is an end symbol, break the loop. If there is only one child. Hold on, let's just find out what's going on here. So print keys. Spell it wrong, but doesn't matter. Python for forever loop, while loop. So I guess if length keys is equal to is less than 1, or the length of keys is greater than oh, if I guess keys is self.end symbol, then break otherwise I guess append the character to the prefix string. And then if there are current dictionary to point to the child. Okay, this is a bit of a funky one, but we did it. Zah! Advanced find matches. Advanced find matches. Maybe we won't even get through graphs tonight. We'll see. Now that we've built the tree class, we want to provide an advanced word filter for locked in to catch variations of bad words efficiently. For example, if the bad word is darn, we want to also filter variations like darn, dufern, and darn it. 1. Assignment. Complete the advanced find matches method. It takes the entire document and a dictionary. Oh god. It takes the entire document and a dictionary of character variations as input and should return a set of all the words in the tree that exist in the document as continuous substrings, even if the word had a variation character instead of the original. For example, the document contains dawn. The variation dictionary contains at and a. Dan is the tree, then dawn should be returned as the match. Okay. So matches equals set. I guess for variation, variant in variations. Variant matches equals I guess self dot find matches. Tip. The advanced find matches method should be very similar to find matches. Oh, we can't use the other one, right? Okay, but with an additional step to check for variants of the word. If the character you're checking in the document exists in the variations dictionary, you should replace it. Document variation with the swap variation before checking if the word is in a tree. Right, okay. Right, okay. Should be very similar to find matches, but with an addition step to check for variations of the word. If the character you're checking in the document exists in the variations dictionary, you should replace it with this swapped variation before checking if a word is in the tree. Variations contains. Dawn should be returned as a match. It should be very similar, but with an additional step to check for variations of the word if the character you're checking in the document exists. In the variations dictionary, you should replace it with the swap variation before checking if the word is in the tree. I guess if in variations, then equals variations. Boom. That was it. Okay. Nice. Well. We got to the end of that. We got 9 lessons in this. Let's see how far we get through this tonight, because don't want to be on it too long. Okay, right, graphs. Let's see how many we get through. So, a graph is a set of vertices and edges that connect the vertices. All trees are graphs, but not all graphs are trees. All trees are graphs, but not all graphs are trees. For now, we use a matrix to represent the edges in a graph that connect to each pair of vertices. For example, here's a matrix that represents the graph above. Okay. In Python, we can use a list of lists to represent this matrix. In any true cell, the corresponding vertices are connected by an edge. Assignment locked. Oh my goodness, just jumping straight in. Locked in, like all social networks, has a locked in, like all social networks, has a social graph. Each user is a vertex, and each friendship, or in corpo speak, connection, is an edge. We want to represent this graph as a matrix. Our users each have a unique ID, which is an integer that we use for their vertex number. So complete the init method. Create a new data member called graph. It should be an empty list, so graph equals that. Fill in the graph with n lists, where n is the number of vertices in the graph. So for fill the graph with n lists. So for vertex in num vertices graph append what's that? Each of these lists should contain n false values. Fill Fill the graph with n lists, where n is the number of vertices in the graph. Each of these lists should contain n false values. Okay. Hold on. Is there a simple way of doing it? Like range, where I don't even have to use the thing. Python for x times so I guess n equals length, number of vertices, range, n, range, n. So I guess for graph I false. I think that's right. Okay, complete the add edge. It takes two vertices as inputs. It adds an edge to the graph by setting the corresponding cells to true. Let's your graph by setting the corresponding cells to true. Whoops. Self.graph. Self.graph. And I think it's going to be u v equals true, and then the reverse. So vu. Okay, I think I nailed that. Boom, not so bad. That was all right. Let's get through these. We might not get to the end of it tonight, but we'll see. Graphs must have a root vertex. Let's read this first. So, graph review. So, edges, vertices. When an algorithm traverses a graph, it typically moves across the edges. Common use case of social networks: user, connection, location, road, computer, cable, tile, path, state, action. Graphs can have any number of vertices. An undirected graph can have up to n brackets n minus 1 divided by 2 edges for n vertices. Vertices can exist without edges, but may be disconnected and thus kind of useless. Typically, graphs, with the exception of multigraphs, can only have a single edge between two vertices. Weighted graphs assign values cost to edges. We'll cover this in a future course. Graphs must have a root vertex. No such thing as a root. That's a tree. What is the maximum number of edges that an undirected graph can have? Slightly more than n, where n is the number of vertices. Slightly less than half of n squared, where n is the number of vertices. Slightly less than n, where n is the number of vertices. Slightly less than n squared. Less than n. Uh-oh. Slightly more than n. Slightly half than n squared, where n is the number of vertices. That one. Explain. N to the power of 2. Oh, I guess, yeah. Sorry, yeah, that's kind of the same. N times divided by half. A fantastic question. So the lesson explains that an undirected graph can have up to n. Yeah, okay. Let's break it out. N, this represents the number of vertices or nodes in your graph. N minus 1 for each vertex. It can connect to every other vertex except itself. So you have n vertices. Each vertex could potentially connect to n minus 1 other vertices. N times, without the times in between, I guess I got confused. Yeah, okay, makes sense. A graph review. What are the maximum number of edges that undirected graphs with 2, 3, and 4 vertices can have respectively? Maximum number of edges a graph can have. So 2 times 1 divided by 2 is 1. 3 times 2 is 6, divided by 2 is 3. 4 times by... wait, hold on. 4 times by 3, that one. Okay. Oh, let's see. Let's see if we can get to the end, but I've got a feeling this is going to be a bit of a minefield. We'll find out. The first assignment, we create a graph using an adjacent matrix like that. Through the rest of the course, we'll primarily use the adjacency list instead. An adjacency list stores a list of vertices for each vertex that indicates where the connections are. So 0 connects with 1 and connects with 0 connects with 1 and 4. Okay, yep. 1 and 4, right. Let's rebuild our graph class using an adjacency list. Complete the constructor. It should create an empty dictionary called graph as a data member. So self.graph is equal to that. Keep going. Cheers, man. I'll keep going. Only got about 15 minutes though, so let's see how far we get on this. So that's fine. Graph, and then complete the add edge method. It takes 2 vertices as inputs and adds an edge to the adjacency list in the dictionary. Be sure to map both vertices. Be sure to map both vertices to each other. It's bidirectional edge. Handle the case where a set for a vertex doesn't exist yet. The resulting graph maps vertices to a set of all other vertices they share an edge with, for example. Yep. Okay. So complete self-edge. It takes two vertices inputs and adds an edge to the adjacency list. Okay, so self.graph graph. And it says handle the case where a set with vertex doesn't exist yet. Okay. So if self.graph u is equal, I guess if u not in self.graph, then self.graph, and then we just do u equals set. Do the same for v. And then self.graph u I guess add v, and then reverse it, so u, then v. Whoops. D, v. Boom. Peasy. So representing graphs, adjacency matrix, that. How does the adjacency list represent the absence of an edge? The nodes list will not contain a reference to nodes that doesn't share an edge with. The nodes list will contain references to other nodes that don't share an edge. False value just won't contain it. An adjacency list would be best stored as a stack of vertices, a single list of vertices, a dictionary of vertices that map to a set of vertices that. Ooh, maybe we could finish this tonight. We're steaming through it. 2 lessons left. Let's see if we can get it down. And then next week, BFS, DFS, P versus MP, and then we'll be done. Let's have a look what those even mean. What does that one even mean? Oh, no. Leave that for next week. Adjacent nodes. So it will be useful to have a helper function to get quick access to the nodes, aka vertices, in the graph that are adjacent to a given node. Assignment: complete the adjacent nodes method. It takes a node, an integer, as input and returns a set of all the adjacent nodes, for example. Okay. No clues, just kind of go hog wild for it. So graph dot graph. So just a simple thing of like return graph gives a node. That? Yeah. It's pretty simple. Yeah, it's quite nice, that. Last one. Unconnected vertices. In locked in, it's sad, but there are users who have 0 connections. Your task is to find these unconnected vertices in the graph and return them as a list. Complete the unconnected vertices self method. It should, hold on. Complete the unconnected vertices self method. It should return a list of vertices inches that have no connections. A vertex with no edges will have an empty set as its value in self.graph. Okay. So I guess unconnected vertices list of vertices, inches on a list. No connection vertices equals. So it's going to be a list. And then we're going to go, I guess, for set in. Oh, I can't do that. Can I? So edges in self.graph. And then say we just, and then return, no connection vertices. Say print. Just want to print out what does it do. So edges. Untouchable outline. I guess vertex. And then it'd say if self dot. So if self dot graph vertex if length of vertex is equal to 0, then no connections vertices dot append that. You could capture that in a variable, but nope, that didn't work. Oh, we didn't even do that. Shaboom. Let's have a look at that solution. Was theirs just as like minimal as mine? Unconnected. So unconnected. Vertex. Okay. Right, so I just did it straight. So vertex and connections. So, right, okay, they split it. So key by key and value. So graph.items. That's okay. Remember to use that. If not connections. Oh, unconnected append vertex. Oh, okay, very nice. Very nice indeed. And tonight, that means we're done. Because no way I've got time to do breadth first search and depth first search tonight. But it means we've only got 2 chapters left, which should mean it's only one. There's only one like night of streaming left, unless P versus MP is going to be crazy. But I doubt it. At least I hope not. In that case, it means we can leave it off here for tonight. And next week we'll be finishing this and moving on to learning memory management in C, which is going to be hell of a roller coaster. We'll see. I think it'll probably only take one night. And for now, we will leave it. Yeah, so thanks for coming down and watching. If you had fun, let me know in the comments. Join us next week, next Monday. Hopefully, I think it'll be the last sort of streaming session on this part of the course, on this module, I guess. And then we'll be moving on to other things. So have a good night and